In this lesson, we're going to start talking about derivatives of logs and exponentials. So a quick refresher on some properties that we may need in order to kind of do some of the derivatives of logs. So big thing about logs is logs don't keep exponents. So if you ever have a log that the value has an exponent attached to it, you can pull it in front and multiply it to the log. Another big one is with the base matches the value, that simplifies out to 1. And then basically, if you have that exact situation, except those two pieces match, this whole thing is going to simplify to x. If you have log of two values multiplied together, you can break it apart into individual pieces normally. And then if you have division, it separates out into subtraction. Normally, in the past, you would have taken individual logs and condensed them so you can solve. In Calc, we're actually going to end up wanting to expand it because then doing the derivative of it will avoid a product rule. So it's just going to be probably a little easier to expand than leaving it condensed. So those properties will come in handy. And then if you do have an exponential that has an exponent with a log and that log's base matches the exponential base, then that thing simplifies out to x. So very kind of similar to this. And then if you want to switch between the two, this is the property for that. So, all right, derivatives of natural logs. We're just going to focus on that in these examples. So we have y equals the natural log of x. And then if you do the derivative of it, it ends up being 1 over x times the derivative of that x. So every single log, every single natural log is going to be a chain rule, right? So let's take a look at a couple examples. So if we have this one, and we're going to do the derivative of it, we're doing the derivative of a natural log, so it's going to be 1 over, this helps to put parentheses around it, 1 over 4x times the derivative of 4x. Derivative of 4x is 4. So you're looking at, if you put this together, you're looking at a 4 over 4x, which then is going to simplify to 1 over x. So there's our first one. So hopefully not too bad. This one, we have a product rule that's going on between the two. So when we do our derivative, we're looking at the derivative of the first, which is 1 times the second plus the first times the derivative of the second. So it's 1 over x times the derivative of x, which is just 1. So we can leave it like that, and then we'll do some cleanup. So this just becomes a natural log of x plus, and this is going to be x over x. So that's just going to simplify out to be a 1. All right, so on the next one, we're going to be doing the natural log of secant. And so if we're doing the natural log of secant, focus that, we're doing a trig. And so we'll do the derivative, natural log. The reason the absolute value exists is because if you remember, you can't log a negative, and the secant can have parts of it that are going to be negative, so the absolute value will make it so it's positive. So it's going to be 1 over secant x, and then you got to do the derivative of secant. And if you remember, we're going to be using pst. All right, so we'll cut out the p and pst. So the derivative of secant is secant tangent. So derivative of this is going to be 1 over secant times derivative of the inside, because the chain rule, which is going to be secant tangent. All right, so let's try to simplify this. So if we clump this all together, we're looking at secant x tangent x divided by secant x. Don't have a lot of space. And the secants cancel each other, so we are left with just a tangent x. All right, and then the last one. So on the last one, we have a quotient rule. It screams quotient rule, but that doesn't mean we have to leave it like a quotient rule. You can actually rewrite it like this. So I'm going to do quotient rule just because that's kind of how it's set up. But if I really wanted to avoid it, because that's just a single value, I could bring it up and it would look just like this. And it's going to be x to the -2. And then I can go through the math on that. But let me do the quotient rule just to kind of show you, here's what it would look like. So if we do the derivative, we're going to do the derivative of the top, right? So we got to be careful because the natural log is a chain rule, or yep, is a chain rule. And then we're doing the quotient rule within that. So no, we're doing the chain rule within the quotient rule. So the derivative of the top is going to be 1 over x squared times the derivative of the inside, which is 2x. All right, so there's the derivative of the top times the bottom minus the top. Put that in there just so I don't get confused. And then times the derivative of the bottom, which is 2x, divided by the bottom squared. All right, let's clean it up. So if we start going through this, we have that x squared is going to undo that x squared. You're just left with a 2x minus, and then that's going to be a 2x natural log of x squared divided by x to the fourth. All right, now it doesn't feel like we can do much, but there is actually a little bit we can do. Squeeze that over here. Is we can take a 2x out of those. So there's a 2x. And that leaves us with a 1 minus the natural log x squared divided by x to the fourth. And I saw if I could take an x out of that, then I can then simplify with this. So I can cross off that x with one of those x's to make it a third. So we have a 2 times a 1 minus the natural log of x squared divided by x to the third. And if we did manipulate this and pull this x squared up and make it a negative exponent, at the end of it, we would go through all the math and we would subtract a power and all of that. We would still get a negative exponent, which then would just come back down to that. So either way you look at it, I don't know if it's necessarily easier, but if you want to give it a try and see if you end up getting the same thing, that would be some pretty good practice to see if you can avoid the quotient rule if you want. All right, so that was doing some derivatives involving the natural log.